Okay, so we continue with the last, what was supposed to be the last talk. We switch the last two talks. Clustered Cepheids in Noma, a distant dwarf galaxy in the plane of the Milky Way. Can you give back the microphone?
Sorry. How's this? All right, so I'm sort of an interloper in the feedback session, and maybe I should hold this like this. Avoid feedback from the mic. But I am going to be talking about work that's related to gas dynamics. I'm going to talk about the recent discovery of clustered Cepheid variables towards the Norma constellation that may mark a dwarf galaxy that I'd earlier predicted. Is this okay, or should I? How's this? Okay, this is good. Okay, so I'm going to talk about the recent discovery of clustered Cepheid variables towards the Norma constellation that may mark a dwarf galaxy that I'd predicted several years ago by using a dynamical analysis of disturbances in the outer gas disk of the Milky Way. So the basic idea is to analyze disturbances in the outer H1 disks of spirals, okay, such as in M51. And I found by applying this method to galaxies like M51 that have optically visible, tidally dominant companions that we can quantitatively recover the mass of the satellite and its location in radius and azimuth. So I'll talk about that briefly. I'll mostly focus on the simulations that I've done to explain the perturbations in the outer H1 disk of the Milky Way. And recently, I've gone through the VVV survey, which is a fairly deep near-infrared survey of the galactic plane, to try and look for this dwarf galaxy that I predicted several years ago. So I think we all know there are a number of discrepancies between simulations and what we observe in the local groups, such as structural discrepancies that have been pointed out earlier. Massive satellites are too dense relative to observations. And I particularly want to point out the observational status quo in terms of the number of satellites that we know about at low galactic latitude, okay? At latitudes less than 30 degrees, we only know of one dwarf galaxy that's such dwarf galaxy. And this is really just the result of the current observational status quo, which may well be related to problems that have been pointed out by the MOND community in terms of the anisotropic distribution of dwarf galaxies. So in this context, it's interesting to ask if we can hunt for dark matter-dominated dwarf galaxies from analysis of their gravitational effects on outer gas disks. So M51 is a great prototype. Here's the satellite on the optical image, and that's where it would sit in the H1. And the basic idea is to do a set of SPH simulations of M51 interacting with satellites. And I look in particular at the low-order Fourier modes of the projected gas surface density and compare it to the data. Okay, this movie shows the gas density response as M51 is interacting with its satellite. And this is one of the best fit simulations, the gas density images as a function of time. And I've marked with a cross the center of the galaxy as well as the location of the satellite. And when we have a good fit to the lower Fourier amplitudes, the satellite sits close to the tip of the short arm as it does in the real system. Now, I got started on this when I was a postdoc at Berkeley several years ago, when Leo Blitz showed me this H1 map of the Milky Way. Okay? And you can see large perturbations in the gas surface density, which can't be explained in a purely isolated context. Okay? So I'm showing here the Fourier amplitudes, okay, of the projected gas surface density relative to the axisymmetric, relative to the equilibrium, as a function of radius. And you can see that the lower amplitudes relative to equilibrium are quite large, therefore 20 to 30%, okay, well outside the solar circle, which can't be explained in a purely isolated context. So we ask the question, what caused these structures? And I started out by doing a grid of simulations of the Milky Way interacting with satellites. The gas density response is shown here, and this is the stellar response. And I varied the satellite masses, the distance to closest approach, the orbital inclination, as well as the details of how we simulate the structure of the primary galaxy. And I'm showing here a variance versus variance plot to give a sense of which simulations best fit the data. Okay, so this is simulation minus data whole squared for the m equal to 1 Fourier mode, and the first 4 modes here added in quadrature, sort of like chi-squared on both axes. Okay, and on this kind of plot, variance versus variance on both axes, the best fits lie close to the origin, which are produced, surprisingly, by a fairly massive progenitor, 1 to 100 mass ratio progenitor, with a fairly close pericenter distance, 5H inverse KPC. And the distance from the origin tells you how poor the fit is. Okay, so this also tells you that a 1 to 10 mass ratio progenitor that gets within 15 kiloparsec wouldn't have produced the disturbances in the outer H1 disk of the Milky Way, which is in fact consistent with analysis of the thickness of the stellar disk. Now, prior work on trying to understand the effects of the known Milky Way satellites is primarily focused on single satellite interactions with either high resolution and body simulations, but these have primarily used ad hoc initial conditions. So recently, I've included the main tidal players of the Milky Way. This is now with gas as well as stars, okay? And these orbits have been derived from the observed HST proper motions. So these are the most realistic initial conditions. These are the most realistic orbits that we can use. And I did this because I wanted to ask the question, are the known satellites enough to explain the disturbances that we see in the outer H1 disk of the Milky Way? Okay, given the known senses, can we explain what we actually see? So on the same variance versus variance plot, okay, I'm marking the effect of the LMC, the Sag dwarf, and the SMC. And you can see that it's far off the origin, okay, and it doesn't exert the known satellites, even with the most realistic initial conditions that we can derive for the orbits, don't exert an appreciable effect on the galactic disk. Okay, the LMC is basically too far away to raise appreciable tides, and the Sag dwarf is an interesting candidate, but its last pericenter was more than a gigayear ago, within which time the disturbances would dissipate in the outer gas disk because it's collisional. Of course, you see structures in the stellar disk, as Chris Purcell has pointed out previously. Okay, so this stream here is the Sagittarius tidal debris. This is LMC and SMC coming in on the first approach. So especially because of this, because I couldn't explain the disturbances with the known satellites, even with realistic initial conditions, a couple of years ago, I was determined to see if I could find this thing. Okay, and a new survey had come out It's a fairly deep infrared survey of the galactic plane. It's about 3 magnitudes deeper than 2MASS. The Vista variables of the Via Lactea, which has light curves in the K-band and photometry from Z through K. So I went through the survey, trying to see if we could find this thing. And I was looking for 2 independent distance measures. Okay, red clump stars have been shown to be fairly good standard candles, as well as, of course, Cepheid variables. All right, so if you can, here I'm using the period luminosity relation of Cepheids in the near-infrared and the K-band. Now, near-infrared light curves have been known to be challenging in terms of classifying variables, so I used a series of successive cuts to try and filter out false positives. Okay, so first I required a high significance in the Lomskargel periodogram. For the sources that pass that first test, I then require a very tightly constrained period distribution. Okay, so I do a parametric bootstrap, and I only retain sources that have a fairly narrow width in the period histogram. And finally, I look at the shape of the light curve. Okay, and I retain sources at that third test that have Fourier parameters that are consistent with known Cepheid variables as observed in the K-band. And there were a few that passed this series of what I would say are fairly stringent tests. And using the period luminosity relation in the K-band, I derive a distance of, on average, of about 90 kiloparsec, which is very close to the current predicted distance of the dwarf galaxy that I predicted several years ago. Now these are, I would still say these are Cepheid candidates. Without spectroscopic confirmation, you know, we can't fully declare victory. I'll also note that there is an overdensity of red clump stars, again, red clump candidates, in the CMD. That is, if you extinction correct and subtract out a background field, you do see an excess at the same distance. So I'll go ahead and summarize. I find that analysis of perturbations in the cold gas is useful for constraining the mass and location of perturbers, whether they're dark or luminous. One of the interesting things about this is that when you're looking at structures in the outer H1 disk, in terms of modeling this, you don't have to worry as much about, say, things like star formation or feedback. Okay, so you have a relatively clean tracer of perturbations. I've tested this method by applying it to galaxies that cover a fairly wide range in perturber to primary gas ratio from 1 to 100 to 1 to 3. We find it works. Very recently, we announced the discovery of clustered Cepheid variables, longitude of -27 and latitude of -1, so closer to the galactic plane than any known dwarf galaxy and at a distance of 90 kiloparsec. So we're currently involved in trying to get follow-up spectroscopic observations. We have to do this in the near-infrared because getting optical spectra is too challenging. And my graduate student is, as we speak, trying to also get I-band light curves to confirm the periods. If it is confirmed, it would be the first dwarf galaxy that was predicted by dynamical analysis to be subsequently discovered. And these kind of systems can yield very tight constraints on the dark matter distribution, and in principle can help to reverse this observational status quo. Thanks for your attention.
Thank you. So we're down to one mic, so you will have to shout.
Yeah, I'm curious about the simulations that you showed of the LIGO and Sagittarius, because to my knowledge, those aren't like fully nailed down. Especially in Sagittarius, what simulations that you showed, and could you elaborate a little bit on what initial conditions are used?
Yeah. So basically I'm taking the observed HSG proper motions and I integrate backwards from the measured positions and velocities. And I sample that range, so there's obviously uncertainty, so I do sample it. So I have an orbital distribution. And given that orbital distribution, I then integrate forward with the SPH code gadget. So at that point, what is left unspecified, given that you've specified your orbital distribution, what is left unspecified are the masses of the satellites. Okay, and I assumed the mass for the LMC from Nitya Kalibal's papers, and it doesn't make a big difference though, because given the distance of the LMC, there isn't that much of a play that you can get with the LMC mass. For the SAG dwarf, there's some earlier work that I did on deriving masses of tidally disrupting satellites. And I assume, it's coming from that, the mass of the SAG dwarf, which is about 10 to the 10 solar masses, which is consistent with the recent observations by Belakurov.
Can you say what the mass of the predicted satellite is? Do you have any idea what the mass of the potentially discovered satellite is?
So the progenitor mass of the putative satellite is about 10 out of 10 solar masses. The stellar, yeah, approximately. So the stellar mass, if you count from the red clump stars, right, the red clump candidates is about roughly several 10 to the 7. Okay, but beyond that, I can't cite, at the moment, I can't cite a.
What was the distance of closest approach?
It's about 7 kiloparsec.
So when did that occur?
It's several 100 million years ago. So you need a massive progenitor that comes pretty close recently. So these are the 3 basic conditions. And that's why, you have to rule out something like the LMC. It's too far away. And that's also why you have to rule out the SAG dwarf. Okay, it is massive enough, and it has a relatively close pericenter. It's just that within the last pericenter, that it was about a gigayear ago, and within that time, the disturbances would dissipate in the outer gas disk because it's collisional.
In the spirit of Kyle's discussion of how robust things are with very different modes, do you have any thoughts about, how these parameters depend on all of the uncertainties?
Yeah, so I deliberately chose, when I was showing the variance versus variance plot, I deliberately chose fairly coarse metrics. And those metrics are not that sensitive to things like the star formation rate and the feedback. And that's actually one of the main advantages of looking at the outer H1 disk as a tracer, right? So things that we don't understand terribly well. I mean, obviously, there's been a lot of progress in modeling feedback. But when you're looking at the outer H1 disk, there's very little molecular gas. Okay, so as a result, you don't have to worry as much about these things as in the inner regions of galaxies. So it's a relatively clean tracer of perturbations. How's this? All right, so I'm sort of an interloper in the feedback session, and maybe I should hold this like this. Avoid feedback from the mic. But I am going to be talking about work that's related to gas dynamics. I'm going to talk about the recent discovery of clustered Cepheid variables towards the Norma constellation that may mark dwarf galaxies using a dynamical analysis of disturbances in the outer gas disk of the Milky Way. So the basic idea is to analyze disturbances in the outer H1 disks of spirals, okay, such as in M51. And I found by applying this method to galaxies like M51 that have optically visible, tidally dominant companions that we can quantitatively recover the mass of the satellite and its location in radius and azimuth. So I'll talk about that briefly. I'll mostly focus.
Okay, So we continue with the last, what was supposed to be the last talk. We switch the last two talks. Clustered Cepheids in Noma, a distant dwarf galaxy in the plane of the Milky Way. Can you give back the microphone?
Sorry.
That I'd earlier predicted. Is this okay, or should I? All right, how's this? Okay, this is good. Okay, so I'm going to talk about the recent discovery of clustered Cepheid variables towards the Norma constellation that may mark a dwarf galaxy that I'd predicted several years ago by using